Welcome back. In this particular module, we are going to learn geometric transformations, in particular the transformations that are spatial, which means that are related to positions of different pixels. It turns out that these geometric transformations are not only a fun thing to do with images, because you may want to rotate an image, you may want to zoom in or zoom out an image, you may want to create special effects on an image. Not only these geometric transformations are just aesthetically appealing to transform an image to one of its variants, rotated image or scaled image or sheared image or any of its combinations, but other than these aesthetics, they are also required to, for example, build very powerful kind of computer vision algorithms that I will discuss shortly. So the geometric transformations, they deal with transforming an image, changing an image to one of its scaled variant, zoomed in, zoomed out variant, rotated variant, translated variant, sheared variant, or any of its combinations. Here I have used a term linear and also a term non-linear. That might be technical, but later on we will see what precisely what do we mean by the term linear or linear transformation, and what do we precisely mean by the term nonlinear and nonlinear transformation. Very technically speaking, this translation, which looks a very simple transformation, you just have to shift the image in some direction and nothing else has changed. This kind of transformation is known as translation. This is also nonlinear, very technically, but we will see later on there is a trick to convert this translation to linear using homogeneous coordinates. And due to this translation, actually the general affine transformation is also nonlinear, but they are normally referred in the umbrella of linear transformations because there is a way to convert these transformations to linear transformations. And don't worry, I will talk about what do we mean by linear transform and nonlinear transform. Let me now discuss some of the benefits of these transformations or some of the applications of these transformations. So there are a lot of applications. Let me discuss just a few. One is to establish point correspondences. To consider you have two images. So for example, this image, and you have another image, maybe a transformed variant of the same image, maybe a scaled variant or some rotated variants of something like that. And let's say there is a point here in this image, and the same point, exactly the same point, is here in this image. If we want to establish a correspondence, which means whether whether this particular point is exactly the same as this point, or we want to search this point on this image, if we can search these points, we can establish that this point is the same as this point. We call this as point correspondence in two different images. I mean, we should not call the two different images, maybe one image is transformed variant of the other. It turns out to establish the point correspondence, we need sometimes to actually match the neighboring patch of a point and the neighboring patch of the candidate point that is assumed to be the matched point of this. And if this particular image, this image, is some, let's say, rotated or scaled variant of the original image, then the patch to be matched is also scaled and rotated variant, and we need to register or we need to nullify the effect of that transformation to get the neighboring patch to match these 2 points. So the point matching actually internally involves to apply these kind of transformations. Sometimes you want to apply the transformation on the source image, and sometimes you want to apply the inverse transformation on the destination image to probably make sure that the neighboring patch are in the same order, and then you may come up with features to actually match those. One such beautiful feature matcher is also known as SIFT, scale invariant feature transform, that we will see later on in this course as well. But To establish these point correspondences, sometimes internally we need to know how to transform two images or the patches of images. And these point correspondences are required to build large panoramas, as well as in stereo it is also required to construct 3D scene out of 2D images. So these automatic point correspondences, they are required for several subsequent tasks. Another thing that is very important is data augmentation, particularly in convolutional neural networks. The data that is available for training a large convolutional neural network is not sufficient, or may not have covered a lot of variety. So one solution to that is to transform the given image into several variants, and some of these transformations are these translations, rotations, scalings, and these kind of transformations. So transform the image and generate new images, and this is called data augmentation. And practically, it is proven to actually improve the performance of a convolutional neural network significantly. And that also requires knowledge of these spatial transformations or geometric transformations. One other thing is building large panoramas. For example, if you want to cover a very large scene in a single image, then there is a trade-off. If you, for example, zoom in your camera, or take your camera to capture great detail of the scene, then you will be only covering a very small field of view. But if you zoom out your camera or go away from the scene to cover a large area in the scene, then you cannot cover that much detail. So what happens normally is, in building a large panoramas, people actually take very detailed images, but they take a series of images, and then it is required to come up with an algorithm that actually stitch these images together and build one image that looks like that one image is taken by the camera, that covers large scene as well as very detailed scene, detailed information of that scene. It turns out that building these panoramas also require these information of both how to come up with point correspondences, as well as how to transform the images in a common space to stitch all the images together. And there are a lot of other benefits as well. So in this module, we are going to talk about all these transformations and their combinations in detail, along with the coding in Python. So let's go in Python and see a simple example of scaling, how scaling can be done in, or you can call this scaling as zoom in or zoom out, how this can be done in OpenCV. And then we will dive in to see what is the algorithm behind this scaling. And then one by one, we will go from scaling to rotation, then to translation, then to shear, then their combination called affine, and so on. So let's dive in to geometric transformations.